So question number B, they're saying use Cramers rule to solve the system of linear equations. And whenever you're given a system equations, that requires us to use Cramers rule. And you're given three letters, there's X, Y, and Z. We are simply going to rewrite the expression so that we'll make matrices. Yeah, so I'll try to just give you a summary of how to do matrices or examples of how matrices are formed. So we have, let's say we have a matrix. So matrices are simply numbers that are in rows and columns. So for example, I give you a 2, a 3, and a 4, and let's say a 6 here. So this here is a matrix. So sometimes they write it like this, or they can just write it using these bars. It's the same thing. They mean the same thing. It's also a matrix. So this is simply a row. This is a row. Then this is a column. That's what you have. Depending on the number of columns and rows, we're going to use those to name the matrix that you have. For example, this is a 2 by 2 matrix. So this is a 2 by 2 matrix. The number of rows, there are 2. The number of columns, there are 2. If I was to give you, to say B is equal to 2, 3, 4. So the number of rows here, there is 1, 2, 3. So it's a 3 by 1 matrix. That's what you have. Yeah, so we name a matrix starting with the number of rows that it has, then followed by the number of columns that it has. So this is simply a 2 by 2 matrix. Now when it comes to addition and subtraction of matrices, so if I give us to say a matrix, this is 2, 3, then say 6 and 4, then there is B, let's say -7, then 8, let's say 5 here. So addition and subtraction of matrices. So addition and subtraction. So the condition for you to carry out addition and subtraction is that matrices, those matrices that you're dealing with, needs to be of the same order. So they need to be of the same order, implying that the order in terms of the number of rows and columns have to be the same. So this is a 2 by 2 matrix, and this is also a 2 by 2 matrix. So we are able to add them. If I was to give you C, C here, let's say it's a 2 and 3. Like this guy here, you cannot add C with any of these other 2 matrices. So the only ones that you can add, if I give it, say, A plus B, this is possible because they're of the same order. Because this here, this is a 2 by 2. This is, let me use a different color. So this is a 2 by 2 matrix. This is a 2 by 2. And this here is a 2 by 1 matrix. So these two are of the same order. No wonder we're able to add them. So write our 2, our 3, our 6, and our 4. We're adding it with 6, 8, -7, and then 5. When we combine them, we add them according to the position that I have. So the 2 is going to be added to the 6. So that's going to be 8. Then the 6 is going to be added to the 8, which is going to give us a 14. Then the 3 is going to be added to plus -7. That's going to be -4. Then 4 plus our 5, which is the same as a 9. Sorry, this is going to give us a 9. This is going to give us a 9. This is what we have. So this is A plus B. That's the matrix that we obtain. So even subtraction will do the same. We subtract depending on the positions that you have. So if we're subtracting A minus B, or B minus A rather, so if we say B minus A, we'll put B first, which is 6, -7, then you have 8, and 5, this minus, there's a 2, 6, then there's a 3 and a 4. So this is going to be 6 minus 2, that's a 4, 8 minus 6, that's a 2, -7 minus 3, that's -10, then 5 minus a 4, that's going to give us 1. So this here is your B minus A. So again, addition and subtraction can only work if the matrices are of the same order. That's basically what we have. The only time we can do anything with matrices that are of different orders, so let's come to multiplication. There is no division, we only have multiplication. So multiplication, we can only multiply if they have they are matching. So in terms of, let's say this is matrix A, this is matrix B, you are only able to multiply these if the first guy, the number of rows by columns that it has, the number of rows and columns that it has. So if the columns in the first matrix, the number of columns is the same as the number of rows in the second matrix, meaning you are able to multiply. For example, the way we had our A, so let me give you 2, 1, 3, 4, and your C, which is, let's say, 2 and a 3, like this. This here is a 2 by 2. This here is a 2 by 1. So meaning you see the number of rows here, and the number of columns there, the number of rows here, the number of columns. You notice that the number of columns in the first matrix is the same as the number of rows in the second matrix. So meaning we're able to multiply. That's the criteria for us to be able to multiply. And if that happens, they'll say find AB, like this, meaning we're multiplying. So we put the first matrix they've given us, which is A. It's supposed to multiply our 2 and our 3. So on multiplication, we're going to multiply row by column. So we'll start by multiplying this row by the column that we have. So 2 is going to multiply 2. That's what we do. That's the first thing. So we're going to have 2 by 2, then plus. You're going to get 1 times 3. That's going to give us 1 times 3. Then down here, because we're now multiplying this row and the same column again, we're now going to have 3 times 2. That's going to give us 3 by 2, which is a 6. Then there's a 4 by 3. So this is going to give us, on top, we just have a 4 plus a 3. At the bottom, you just have a 6 plus 12. And this is going to give us a 7 and then 18. So the answer we are getting is a 2 by 1 matrix. That's A times B, which makes sense because A was 2 by 2 and B was 2 by 1. So because these guys are the same, we're able to multiply. The answer that we're going to get is going to have the following order. The rows will be 2, the columns will be 1. This will be the answer that you get, which is this guy that we've gotten here. So on multiplication, we always do row by column. That's how we do it. So if it was a 2 by 2 type of setup, if you have A, let me just use small numbers, 3 and 4, you're multiplying it with B. With B, that looks like this. So B, let's say you have a 4, a 3, then you have a 2, and then negative 1 here. So if you're multiplying A times B, 1, 3, this is negative 2, 4. So these are 2 by 2, meaning even the answer is also going to be 2 by 2 because this is what? This is 2 by 2, right? Even this is 2 by 2. We're able to multiply because these numbers are the same. That's what you have. Then we're expecting our answer to be 2 by 2 because the number of rows is 2 and the number of columns there is 2. So this tells us that we're able to multiply. Then what remains, the number of rows and columns that remain tell us what the answer is going to look like. Yeah, so that's basically what we have. Then if we do the multiplication here, we're going to go through the row by the column. That's what you have. So we'll start with 1 times 4, that's a 4, plus 3 times 6, that's a 9. So we have that. Again, we do row again by this other column, this side, to put the number here. 1 by 2, that's a 2, then plus 3 times negative 1, that's a negative 3. Then we are done on top. So we are done using the first one. We now come at the bottom. Then we do row by column again. So it's negative 2 times 4, that's negative 8. Then plus 4 times 3, that's simply going to be a 12. Then again we do row by this column here. So negative 2 times 2, that's negative 4. Then plus 4 times negative 1, that's a negative 4. Then this is going to give us a 9, that's going to give us a 13. This is going to be a negative 1. This will be a 4. Then this will be negative 8. So this here is A multiplied by B. So this is how we multiply matrices. And the condition to multiply is that the rows of the first matrix, the number of columns, I mean, for the first matrix, this is row by column, the number of columns here must match the number of rows in the or on the second matrix. That's the condition. If they are not the same, meaning we are unable to multiply, that cannot happen. Yeah, so this is what we have. Now, matrices are important because they are also used to solve simultaneous equations. But before we talk about simultaneous equations or the application of matrices, there's what we call determinant. So if I give you a matrix, let's say this is, I'll put letters A, B, then C, D. So the determinant of a matrix written with these bars, this means the determinant is the same as the major diagonal, which is A times D, minus the minor diagonal, which is B times C. So this guy here is your major diagonal. That's what you have. We call it the major diagonal. And this is the minor. So we're just going to say A times D minus B times C. That's what gives us the matrix, the determinant of a matrix. Yeah, so if I give us A to be 2, 3, 4, 6, the determinant of this is simply going to be, these are just supposed to be straight lines. The determinant will be 12 minus 12, which is just going to be a 0. So it happens to be a 0 because 2 times 6 minus 12, this will just give us a 0. That's what you have. Then the way they gave us this 3 by 3 matrix, these are equations whenever you have 3 letters like this. So this is this is the determinant for a 2 by 2. This is what we get. This is what we do. But the determinant for a 3 by 3, so let me write it to you. Determinant for a 3 by 3 matrix, we get it. So we have, this is, let's say this is A. Let's call this A1. Let's call this A2. Let's call this A3. Let's call this B. For the second line to be B's, there'll be B1, there'll be B2, there'll be B3. Let's call this C1, C2, and C3. So if this is a 3 by 3 matrix and you want to get its determinant, so the determinant here is just going to be A is equal to, or the determinant of A is equal to, you hide the first column. So we hide this. We're simply going to hide this guy here. So hide this. We'll just say this is encompassing this row and this column there. So we're basically going to say A1 multiplying, this is the determinant of what remains is B2, then you have B3, and you have C2, and you have C3. Then you're going to say minus, so we have already used A1, then we come to A2. So A2 is here, meaning we'll hide the row that it's in and also the column that it's in, implying that we're going to say minus A2 and then get B1, C1. So this is B1, C1, and then B3 and C3. Then plus, we go to A3 now. So we're on A3. If we hide A3 like that, we're simply going to hide the row that it's in and the column that it's in, meaning we're remaining with this. Then we put these guys here. We have a C1 and you have a C2. So this will help you to get the determinant, because this is now going to be, you get the determinant of this matrix. This is now a 2 by 2 matrix. Yeah, so if I give you an example, maybe this will make sense with an example. I give us A, something very straightforward. There's 2, there's 1, there's 3, there's 4, there's 5, there's 6, there's -1, there's 2, there's 3. Yeah, so let's say there's this. This is what you're having. To get the determinant of A, this 3 by 3 matrix, we're simply going to say we start with 2. So we say we put the 2 outside. When the 2 is hidden, what remains is this part here. So the row and the column where 2 is found, we ignore them. So we're just going to remain with a 5, then a 6, then a 2, and a 3. Then minus, we put the 4. So it's always minus here. You put the 4. Then we're going to have 1, 3, then 2, and a 3. We hide the row and the column where 4 is found. Then this was supposed to be a plus, but then we're having a negative 1. Then we're going to say we hide the row where 1 is and the column where 1 is. So what remains is 1, 3, 5, and 6. Then from here, we'll just bring the 2 there. What's the determinant of a 2 by 2 matrix? We say the major diagonal, which is 5 times 3, that's a 15, minus the minor diagonal, which is 6 times 2, which is a 12. 4, then we have 3 times 1, that's a 3, minus a 6. This is minus 1. Then 1 times 6, that's simply a 6. Then minus, that's a 15. This is simply going to be 2. 15 minus this is a 3. Minus 4, this is minus 3. Minus 1, this is negative 9. Then this will simply give us a 6 plus 12, then plus 9. This is going to give us a 27, if I'm not mistaken. So this is going to give us 27. So that's the determinant of a 3 by 3 matrix. That's how we get it. Yeah, so the reason why I'm showing you this is because we need this skill for the determinant for us to get the answers to the x, y, and the z that is given here on the Cramers rule. So whenever we are dealing with Cramers rule, we are going to isolate the coefficients of the letters given. In short, we turn the equations into a matrix. So this is what happens under Cramers rule. So you're given 3 equations. So meaning we're going to write what's the coefficient of x there. The coefficient of x is 1. What's in front of y here is negative 2. What's in front of z here is just a 1. Then what's in front of x there is a 2. There's a 1. There's a negative 1. We have a 3. There's a 2. Then there's a 4. So this is the matrix that we're going to be dealing with. Then we have another matrix with these numbers here. Let's call it x. So we have A. Let's call this guy A. Then we have x this side, which is going to be composed of 4. Then there's a 5, and then there's a 3. So you always make sure that the letters are arranged in this order. So the x constant coefficients are here, the y, then you have the z ones this side. So that's what you have. This is the first step in Cramers rule. You always do this. Then the second step that we have to do is to get the determinant of this matrix. Yeah, and if we want to get the determinant of this, we use the previous method that we're from doing for a 3 by 3. So pause the video and attempt to do it. We see the answer you're going to get. Okay, so we get the determinant of A first. So we're looking for x, y, and z. Those are the letters that we are trying to solve for. So we get the determinant of A first. This is going to be, we say 1. Then when we hide 1, the row and the column where 1 is found will only leave us with this part here. So let me indicate it. So when you hide 1, you're using 1, so meaning it leaves us with this part here, this portion. So that's where the 1, the 2, the negative 1, and the 4 are going to come from. Then negative 2, if we are using negative 2, we are going to hide the column and the row where negative 2 is found. So if we do that, we're going to have, let me use something else. So the row, we're using negative 2. So meaning we hide the row and the column where negative 2 is found. So the only thing that remains is this part here and this part there. So that's what is going to be here. There's a 2, 3, negative 1, and a 4. That's what we get. The formula is always having a minus here. So it's the first thing, you put the matrix, then minus the second thing there. Then it happens that it's also negative. So have that, then plus the last thing, which is a 1 as well. Then we are having the row and the column where 1 is found. So this is just going to be, if we hide, we are using 1. So the row and the column is hidden. What remains is this part here. So we're going to have a 2, or there is we're going to have a 2, a 1, then the 3 and the 2. So that's what we are having. Then here we can proceed. The determinant here is just going to be 1 times 4, which is a 4, minus 2 times this, which is a negative 2. Then this is a plus 2. Then this is going to be 8, minus negative 3. Then plus 1. This is going to be a 4, minus a 3. And this is just going to be your 4 plus 2 times 1 outside. There's a 1, then there's a 2. This is going to be 8, 9, 10, 11. This is going to be a 1. This will be a 6. This will be 22 plus 1. This will be simply giving us a 29. This is going to be a 29. So the determinant of A is actually 29. We keep it there. So once you get the determinant of A, which is your 29, we have to start replacing each column. So we've gotten the determinant of A. We have it. Now we have to create 3 more matrices. So we can just keep it here. The determinant of A is equal to a 29. We keep it there. So after finding the determinant of the matrix A, we're going to be replacing each column by the X matrix this side. So you have the letters X, Y, and Z. So these were the coefficients of X, Y, and Z. So we're going to create 3 more matrices. So we're replacing the first column by the matrix of X. So we're just going to call it AX. The matrix we are creating is going to be called AX because we are replacing the X column by the matrix of X this side. So we're going to have, this is going to be negative 4, then we have 5, then we have a 3, then we put, so we have replaced this part, but everything else remains the same. So this is going to be negative 2, 1 and a 2, this is a 1, 1, then this is a 4. So we're going to get the determinant of AX, and we're also going to create the matrix of AY, meaning we're replacing the Y column by simply getting the matrix here and replacing the middle part. So this is going to be 1, 2, this is 3. So the middle part has been replaced by this. So maybe I should be indicating here. Let me just try to write this. 1, 1, 4. Then we're also going to have AZ, which is going to be, just a minute. This is a 1. This is a 1 and a 2. So we're just recreating this. Yeah, so we're saying on the first column, if we were calling it AX, we need to replace with negative 4, 5, and a 3. Then here on the second column, we replace with negative 4, 5, and 3. Here on the last column, we replace with 5 and 3. So these are the 3 matrices that I was talking about that we're going to create. Once you create them, we now have to get the determinant of each matrix. Yeah, so when we get the determinant of this, so AX, we need to get the answer here. The determinant of AY, we need to get the answer here. The determinant of AZ, we have to get the answer here. So when you solve for the determinant of this matrix here, 3 by 3, you can confirm that the answer you're going to be getting is a 29. And also when you solve for AY, you check that the answer you'll be getting for the determinant will be 58. Then for AZ, the answer will be negative 29. That's what you'll get. The same procedure that we're doing to get the determinant of A is what you use for AX, AY, and AZ. Then once you're done, you can now try to get or to show how we get the values of X, Y, and Z. So to get X, we just say the determinant of AX divided by the determinant of A, which is just going to be a 29 over a 29. So that's how we get the 1. Then to get Y, we'll just say the determinant of AY over the determinant of A, which is just a 58 over 29. So this is going to give us a 2. And to get Z, we'll say the determinant of AZ divided by the determinant of A, which is just going to be negative 29 over 29, which is just a negative 1. So implying that, or therefore, X is equal to 1 and Y is equal to 2. and z is equal to -1. So these are going to be the answers of your Cramers rule equation. These are this system of linear equations. So you know the value of x, y, and z. You can always confirm whether the answer you've gotten is right by replacing. So we can just check using the first equation. Where there's x, we can put a 1. Where there's y, we can put a 2. Then this side, where there's z, we can put the answer we've gotten, which is it a -1? Is it? It's a -1. So when you sum up this, you're simply going to get a -4, which is this answer on the right hand side. So this is how we answer questions that have to do with Cramers rule. So to just verify that you understand what you've done, can you attempt to solve 2x plus 3y then plus z to give us 10, and also 4x plus y then plus 2z, this is equal to 15, then also 3x plus 2y plus 3z, this should give us 18. Can you try to solve this one in the same way that we've solved this question that we're doing, this example here? It's the same thing that we need to do here. So tell me the values of x, y, and z. So that's what we are going to do. So try this, then send me the answer, then we see if you understand the concept. So to make life easy, you can actually use a calculator. By the time you're done, you should get your x to be 25/15, which is just the same as 5/3. Then you can also, your y should be 1 by the time you're done, and your z should be 55/15, which is just the same as 11/3. Yeah, so you can even use a calculator to just make things a bit faster. So try to see if you can get these values, but send me the working.